All right. So today, I think we should be able to get this done in one day. We'll talk about repeated measures designs. And you'll see today that repeated measures designs are actually a special case of a type of design, a more general type of design. Okay? So, let's say you're interested in learning or forgetting. So you have to look at change over time, right? You can't really do independent groups with that. You can't say this group is going to have this many trials and this group is going to have this many trials. Let's see how the learning happens between the two. It's a weird comparison to make. It's much more sensible to do a comparison within individuals, so I can look at how you forget things over time or how you learn things over time. It makes more sense to do it. I'm not saying you can't do it that way, but to me, it doesn't really fit the bill, so to speak. It's probably better if we test the same people over and over again, right? Okay, makes sense. So we're going to look at change over time in something, which is something we look at. So you get something like this. We get retention intervals, let's say of 5 minutes, 1 hour, 24 hours, and we get the same group in each cell. So this is different now. We don't have different groups in cells. The design now looks like this, where we have retention interval as our independent variable. Is percent correct or something, remember. And then group 1 it's all the same people. We're tested over and over again. Okay, so that's the point is, there's a potential problem here. I've been harping on about how independent observations, how you must have the same independent observations. Now we don't have those. We have dependent observations. Think about it. Right? I can make a pretty good guess at someone's score in one retention interval if I know who the person is, because I can see their scores at the other retention interval. They're completely dependent. They're the opposite of independent. Oh. But that's supposed to be bad, because there's nothing in the model that says that we can have that. Well, why would you put the model in? The nice thing is here we know how the dependence works, right? So I know that if I have Sam's score, the next time the level of the variable we'll call humans or people, and we'll call it the Samantha McCormick level. I got that again. I say that because we have the two Samanthas. One thing you learn when you teach a lot is that names become popular for very brief periods of time. No, I'm serious. It's really interesting. It's really, really interesting how, like, when my brother had their second kid, who would now be the age of most people in this room, they named her Taylor, and it seemed like a really weird name that no one had ever heard of before. And now half the class is named Taylor. Like half of the women are named Taylor. And we'd never heard of this name. And I think my brother thought he invented it. No, it's one of those things. It's only two Samanthas. It just happens. My name's boring. It's Dave. Though, there's a lot of guys my age named Dave. All the way through school, I was David B. Even in graduate school, I was David B. My first email address was davidb@psych.utoronto.edu. That's right, I'm old enough that I had a .edu address in Canada. Pretty impressive. Anyway, let's put that in the model. So our model now looks like this. X equals mu plus tau plus pi for people, plus epsilon. People, different levels of people, the Samantha McCormick level. And various the Brie-Bennett level. We have very different levels of people. Any score equals the grand mean plus the treatment effect. This all looks the same as we've seen before, plus the effect of error, plus, like that slid in there, the effect of subjects, or I always think pi for people. Determine the model is people. Silent green, nobody, nothing. Okay. I just spoiled a 40-year-old movie for you. 45-year-old movie. So Soylent Green is people. You didn't watch the movie yet. So what we've done now is we say, look, we got this other variable, people, subjects, whatever you want to call them, and we can actually put that in. Now, we wouldn't call it the semantic level. We'd say it was level 1 of subject, level 2 of subject. That's making no judgment at all. You can do it. I promise. I do make judgments about all of you all the time, but I keep them to myself. Actually, that's not true. I write them on pieces of paper and hand them back to you. That's what I do for a living. I mean, I'm sorry. I literally discriminate against everyone for a living. Like I put people into categories. That's what discrimination is. I do that for a living. They pay me handsomely almost, really. Almost what I'm worth now. Anyway. It was a strange little place I went there. I'm back though. Okay, so the design kind of looks like this then. It really, instead of, we now think of it kind of as a 3x4. We get 4 people per group, or 4 people we're testing. We're testing 3 times. So we actually have, really, while it's a single independent variable we're interested in, we really have 2. One of them is the subject. So that's an important thing to take care of, or sort of keep in mind when you are setting this up using something like SPSS. The version of SPSS that we have doesn't deal with repeated measures very well. But you know what the nice thing is? We can fool it. We can put in a new variable called S for subjects and give it 1, 2, 3, 4, 1, 2, 3, 4, or whatever, and then just throw that in the model. It can, SPSS doesn't know where the numbers came from, so it doesn't care. It's a nice, easy way to do it. I actually kind of like it better than the way that SPSS does it at the box when it does repeat it, because it does it in a very strange way to my way of thinking. As I said, I'll show you the set of a data set on Tuesday. So we've decreased error. Let's put the model back up here. X equals mu plus tau plus pi plus epsilon. The regular model that we're used to for just a one-way analysis of variance is that. So we've made errors smaller here because the only place that this pi thing can come from is it can come out of the error term. It's the only place it can come from because mu's there and tau's there. So the only place it can come from is out of error. That's good. Making errors smaller is good because what do we divide by in analysis of variance? We divide by mean squared error. We divide by this thing. If we make that thing smaller, if you make the epsilon term smaller, it makes the f value bigger. Makes the fraction bigger. Bigger fraction, easier to find significance. Right? So that's great. But we paid for it. There are no free lunches in statistics. You know that when we separate out sums of squares, source of variation, we also separate out degrees of freedom. So, in fact, we have fewer degrees of freedom than we had before. And if you look at an F table, the smaller the number of degrees of freedom, the smaller the F value. Okay? The critical F value. You know how much I paid for this damn brony shirt for my son? Then he decided he didn't like My Little Pony anymore. So it's like, screw that, I'm keeping it. It's a perfectly good t-shirt.
How much was it?
$35. Plus shipping.
Was it like from Etsy or?
No, it's from some My Little Pony fan site in the States. He loved it for like 3 years. He was way into it, and he was like unashamed about it, which I thought was really great. Then I always say to him, "You like what you like. You don't ever apologize for your taste." I say that to everybody. I don't have to like your taste, but you don't apologize for it. You want to eat your steak well done, you're a Philistine, but that's the way you like your steak. Same sort of thing. And then he's like, "I don't like it anymore. It's for babies." Oh, jeez, there's 2 of them, by the way. I have another one too. So now and then I'll be wearing this t-shirt and I'll be at somewhere and somebody goes, "Cool, man, I'm a brony." Just like, no, not me. It's my kid. He even grew out of it. Just it's a pretty quality t-shirt though. Anyway, again, going off weird places, coming back. So we've decreased error. That's good. We pay for it with degrees of freedom. We pay for it. Okay. So, and to make that maybe a little more clear, if we did it with a regular one-way ANOVA, this design I had which is a 3-level. If we looked at it not like it was repeated measures, but like a regular analysis of variance, which you could do, you are violating assumptions, the assumption of independence of observations. You'd also, your error term is all these degrees of freedom, which is great, but it's also way bigger. This is a better analysis. Retention interval, subjects, and error. The subjects have 4 degrees of freedom. 3 degrees of freedom. We have 4 subjects. Lose 1 for fixing a mean. Okay. So we could do, what we do is the one on the right. The one on the left isn't necessarily wrong, it's just not as right. It's not as accurate. You're gonna miss stuff here, you're gonna find stuff here if something happened. It's not like it's horribly wrong. Okay, questions? Okay. So any design has a finite amount of variation, a finite amount of degrees of freedom. And it's how we split them up that matters. So we've partitioned degrees of freedom and variation a little further. That's really all we've done here because we could put a new term in the model, pi for people. Pi for the people. All the people should have pi. Mean squared for retention interval would be exactly the same, or mean squared trig would be exactly the same in both analyses. It would be literally the same number. It'd have the same number of degrees of freedom, and the sum of squares would be exactly the same. So you get the same mean square. You literally would. In fact, I believe that's the assignment that I posted that's due on the 14th, is to do it once as a regular analysis of variance, and then do it once as repeated measures. Yeah. Yeah, that's right. So that's on my website, and you'll see that. You'll actually see the mean squares exactly the same. The question you always have to ask yourself is the reduction in mean squared error, again, making that smaller is good because we're divided by something. Is that worth it because we paid for it with a loss in degrees of freedom? And again, if you look at an F table, the degrees of freedom that are available, the critical value gets bigger when you have fewer degrees of freedom. It's easier to exceed a smaller number. So when we have more degrees of freedom, we have a smaller number, right? So we've paid for something. We've got something out of it, but it, well, I guess it wasn't for free. So the question you always have to ask yourself is was it worth it? And the answer is almost invariably yes. Okay? Almost invariably yes. Okay, questions so far? Good? Now, you got to think about this a little bit. Is it realistic to think that this is actually true? X equals mu plus tau plus pi plus epsilon. In this case, because it's the same people every time, right? So we don't use Samantha anymore. It'll be Bree, so it's always Bree. It's always Hest and Bree over and over again. The Bree-Bennett level of humans. And let's compare Bree to Enya. Okay, fair enough. Do you think both of you actually, the way retention interval affects both of you is exactly the same? It seems really unlikely, doesn't it? Some people's memory just doesn't decay as quickly as other people's. I'm not making any comment about our two friends here. We could, however, say compare me and Paul. I remember things forever. And Paul can't even remember where he put his shoes. And they're on his feet. Things just decay. It actually makes no sense to say that they're even. We're missing a thing here. The thing we're missing, in fact, is the interaction of treatment with person or treatment with or tau with pi. In other words, I forget things less quickly than Paul does, even though I'm older than him, because I have a superior intellect. See, I turned it that way rather than make any comments about our friends. Also, the thing I was saying about me and Paul, it's true. So, I don't have to make anything up. I'm just smarter. Yeah, there really should be an interaction, actually, shouldn't there? There really almost has to be. It's crazy to think this would be true. It's possible, it's just, I can't think of a lot of variables where they affect everybody exactly the same way. The level of person changes the level of treatment. Oh, that sounds exactly like an interaction. Or change the effect of treatment, that's an interaction. So, well, we've got to put that in the model. So our model changes, in fact, from this sort of idealized version to this version, x equals mu plus tau plus pi plus tau pi. Right, tau pi, it's delicious. Flaky crust. Thank you. X equals mu plus pi plus tau pi. Starts to sound like we're some sort of sorority. Yay, tau pi! Yeah.
So why don't we have error? Okay.
There's no error? Yep, no error. There actually is error. We just can't, we have nothing left over. Epsilon, the error term, is what's left over when we've got everything in the model. We don't have anything left over now. We've exhausted the degrees of freedom in the variation. That's what's happening. I love when someone asks that question because I have the slide ready. Make you so happy. Yeah, we've exhausted the degrees of freedom. In fact, the way you calculate the error, the epsilon term, is exactly the same way you calculate the interaction of tau and pi. Like, it's literally mathematically the same, or arithmetically the same. So all we've done really is just turn this, we've renamed this term in some respects. That's all we've done. So we're treating S subjects, we're going to call it S, as just another or N, whatever. We're treating it just as another variable. The math doesn't know that the variables have the levels Bree and Enya and Sam, and Dave and Paul. It doesn't know that. It's 1, 2, 3, 4, and 5 as far as the math is concerned. So that's all we're going to do. We're going to do just exactly what the math would do. So in fact, we get this. So with our example we had is we got retention interval subjects, retention interval by subjects in total. Notice how these degrees of freedom didn't change from what we had before. And in fact, the mean squares wouldn't change. Literally wouldn't change. If we start including subjects as a factor, which we will do shortly in everything we do, you'll see that, in fact, even the most simple analysis of variance has an error term that is, we don't have an epsilon anymore. We don't have an error term so much as we have, like, it'll be something like subjects nested within groups or something like that. Oh, I see what happened. So that's a teaser for the next couple of weeks. Excited? I am. I've taught this class so many times, I don't know if I've said things or not. Have I made that joke before, like that kind of thing? That literally, 1 year in Newfoundland, I taught 3 sections of intro psych. I had no idea where I was. Half the time, I'd be getting up and I'd be saying, okay, did we do this? Didn't I just do this? Well, that was those guys. There was a night section, they were okay. There's 1 chapter a week. But the 2 day sections, I get in. It was all in the same room, too. It's awful. This is different. The proactive interference that builds up, though, over 20 years is something. So we're just treating subjects as another variable. That's all we're doing. Okay. So how does this work? Well, our error term is actually a treatment by subject interaction. That's what we're going to divide by one thing by the other. Remember I mentioned all that crap about fixed and random factors and said there's a reason I'm doing this? This is why. Subjects are a random factor. They aren't a fixed factor, and they're the closest thing we have to a random factor because we aren't really randomly selecting levels of people, but we're not doing fixed. That's for damn sure. It's closer to a random factor. So that's why we're doing that. The expected values worked out. There's actually a reason I went over that mixed model crap last time. So we have like the expected value of mean squared treatment is going to be treatment plus, or just treatment. And the expected value for mean squared for subjects is going to be this. Right, because it's a mixed model. Okay? And the expected value for subjects by treatment is going to be the interaction term treatment. How would I put it? Oh, look, we can divide mean squared treatment by mean squared subjects by treatment. We can isolate that and get the tau effect. Okay. That's why I talked about that mixed model stuff the other day. Well, that's the big reason. The other reason is I had time to kill. I thought I talked about it. No, I didn't have time to kill. I have time to live. There's a lot of things I just say to myself that are really funny to me because I'm referencing like 85 other things in my head. But to explain them, A, you wouldn't find them funny, and B, you would just think there's something wrong with me. So I just leave it where it is. But you know, though, sometimes I'm laughing, and I'm not laughing at anything you're doing. I'm laughing at what an idiot I am. So we don't test the subject factor, do we? So the expected value for mean squared subjects, or mean squared S, if you want to call it that, is just pi. It's just pi on its own. It's just delicious pi. And you look at it and you go, how do we test that? We can't isolate. It's just on its own. We can't determine if it's significant or not. We can't. It's impossible. It can't be done. So people are, we just leave it there? Yeah, we just leave it there. You can't test mean squared for subjects. There's no error term with the correct expected mean square value. What would that even be? I guess we'd have to divide it by, no, there's nothing there. What the hell are we going to do? Now the question I could ask you is, who cares? Oh, are you going to come up with the exciting scientific discovery that people are different from each other? Ooh! Call the Nobel people right away. Stop the presses. We're going to publish this in Science and Nature. People are different. It's not even interesting. Besides, people are people. So why should it be Depeche Mode? Nothing, nobody? I'm so much older than all of you. It's not interesting. We can't do it. It's physically impossible. It's mathematically impossible. Plus, it's uninteresting. It's the ultimate thing of why would anyone do this? It's like, again, it's like taking a course with Paul. Why would anybody do it? It's not even required at this point. Apparently, he shit on me all last year when I was on sabbatical. I couldn't do anything with it. So, payback time, buddy. And my stuff's on the internet, and people can hear it forever. Okay. Okay, do you understand the logic then behind these repeated measures designs? It's basically like the correlated t-test or the dependent sample t-test. It's the same idea. In fact, really, it's kind of an extension of it. These designs, these repeated measures designs, are a special case of something called a randomized block design. And you're saying, why do you teach about randomized blocks first? Because it would take twice as long. Seriously, because explaining the logic of this after thinking about repeated measures makes more sense, at least to me. So, we talked about the matched pairs or correlated t-test, a couple slides back in January. It's March. We use the before and after, subjects as their own controls. Matched pairs. Oh, matched pairs. What about matched pairs? We would think of matched pairs. What about like groups of, so we can do the same thing. We can extend this into, not matched pairs, but let's say we have 3 levels of a variable. Let's do matched trios. Right? So we've got Samantha and Enya and Bree. And we find out they're the same on some variable, enough that we're going to treat them as their own controls. So subjects usually matched on the dependent variable, just like they would be matched on the dependent variable in a correlated t-test or a repeated measures t-test. Right? That's all we're going to do here. This is not anything fancy. It's basically the logic is exactly the same as the repeated measures t-test. Or, repeated measures t-test, repeated measures ANOVA. We're just extending it now to using groups or blocks of people. So we'll do the same thing that we did with repeated ANOVA. We'll do blocks of people as our own controls with analysis variance. What do we need? We need something called homogeneity of experimental units. What do we need? Homogeneity of experimental units. What do we want it? Now. So, what that means is you're the same homogeneity on some variable. And that's the external units are the Samantha and Brie. That's the people within a group, within a block or so. It's funny, it used to be when I saw ANOVA, I just thought analysis of variance. Now I think about my immersion circulator. Got a thing for doing sous vide cooking. You know what that is? When you take a water bath and you keep it exactly the same temperature. And you got food in like a bag that's sealed, and then it's in water, and it doesn't get wet. It just gets cooked exactly at this one temperature. You leave it there for hours. Then you take it. It's amazing. The restaurants do it, and the one I have is made by a company called ANOVA. I had to buy it. It was like saying, "Hey, if you cook," and this is named after a statistical test. Doing some steaks with it tonight. Anyway. There's a few ways we can do this. Litter mates, well, you guys are litter mates, or matched pairs, twins, but you might, here's an example. I have, I think, a decent example coming up. We're going to block people on what we consider to be a nuisance variable. It's a variable we can measure, and we know it's going to have an effect, so we just want it removed. And we would know that all these three women here have the same level of whatever that nuisance variable is. So we call it a nuisance variable. It's something we block on. This is going to reduce this error, and it's going to give us greater statistical power. The block part, instead of people, the block part now, that's what would be the pi part here. Okay? It's going to give us greater power. And I got, like I said, I think a pretty decent example coming up which should explain this to you. The structural model actually looks like the first one we had for repeated measures. So it just looks like this. Any score equals the grand mean plus the treatment effect plus the effect of being in a block or having that level of that nuisance variable plus the error, the residual, the stuff we can't explain. Okay? The examples coming up. Question? So here are the assumptions. Some of the treatment effects is 0. That shouldn't surprise you. That's always been the case. Errors normal and independent with a mean of 0 and variance of sigma squared sub epsilon. It's been the case all the way through. And the blocks, the effect of the blocks, are normal independent with a mean of 0 and a variance of sigma squared sub pi. That just means they're deviations from 0. And they're independent of each other. Those are very standard assumptions that you would have seen before. Errors are independent, so the error is independent of the block. That's an important consideration. And that block is independent of treatment. There's nothing in that model, there is no tau pi. We can only really do that with in the special case where it's repeated measures among the same people. When we're doing blocks, we can't really throw that in there. Okay? So error is independent of pi. There's also no interactions, no tau pi interactions either, none. That's the most poorly worded thing I've ever put in the slide. No interactions, no tau pi interactions either. None of them are there at all. There's no interactions in this stuff, which is really annoying. There's a way to do it. It's a very long. We go to graduate school. If you want to learn about that, that's fine. It's just not something you typically do. Okay. Here's my example. Oh, it's not here yet. It's coming up. What do we do if there's an interaction? Well, if there's an interaction, error is going to increase because it's the only place you can go. So if there's a tau pi or tau epsilon or pi epsilon, interaction, the only place it can go is into the error term and make it harder for us to find an effect. So you're going to lose power. So this is our model up here, x equals b plus tau plus pi plus epsilon. What if there's something else that we haven't accounted for? Well, the only place it can go is here, the leftovers, residual. It's the only place it can go, which means it's going to be that bigger. That's what we end up dividing by, and it's hard to find the difference, which sucks. Because maybe we had something. So don't have interactions. But Dave, how do I know if there's any interactions if I can't test for them? Well, I just suggest not having them. There's really no way to do it. The only way to do it actually is have look at a graph and see if it bugs you. So what do we have here? We've got, the example I came up with here is there are 3 methods for teaching. And let's say it's for teaching French as a second language. Okay. So it's French as a second language teaching. Method 1 is, I don't know, rote memorization. Method 2 is role-playing, dialogue-y things. And method 3 is move to Jonquière. I don't know, I picked somewhere really French. So, or Boucherville, where my in-laws live. There is no, Paris is not as French as Boucherville, Quebec. It's the most French place I've ever seen in my life. It's incredible. So short, right across from Montreal. Montreal, it's like not like you there. It's like there's no English people anywhere. Which that's not really the problem. Which is surprising. But you would think we have people that have different levels of French education. We could block on that. Some people only ever did French up when you have to keep doing French to grade 10. Is that right?
Grade 9.
Grade 9. Way to go, Ontario. So. Pourquoi est-ce que tout le monde ne parle pas français ici? That was me speaking French poorly. I don't actually speak like that. We got people who just went to grade 9. That's one block. We got people who did French immersion. That's another block. And then we have people who did French, actually went to French school. That's a final block. You might expect people to, you'll say, oh, I see why you do that. Because the different levels of experience, low, medium, and high, would certainly have an effect on how you learn something, or it could. So we blocked on that. We only had 9 people. And we got 3 that have the up to grade 9. We have 3 that did immersion, and we have 3 that actually did French school. And you're going to look at that and say, okay, here's my question. Is there interaction there? Sure, of course there is. The lines aren't parallel. Now, is it enough that it would bother you? Well, frankly, if you find the effect, it doesn't matter. If the F value comes out significant, you shouldn't care. If the F value doesn't come out significant, then you go, it may be because of this interaction, damn it. Like, that's because you couldn't find, because you lost statistical power. If the lines cross, you do find another research design. Problem is, you're doing this afterwards. It's too bad. Questions? So the randomized block is the general case of the special case is the repeated measures. We don't usually do randomized blocks, but it really theoretically is the more general way of thinking about repeated measures. Okay. You could have more than one repeated measure. Oh, a 2 by 3 with all of them within subjects. In other words, same subjects get every level of the variable. we got implicit and explicit memory tests. So implicit is word fragment completion, and explicit is recall. So if you in this room just want to test on things like that, one of you will be.
Thanks for reminding me.
And 3 retention intervals, 5 minutes, 1 hour, 24 hours. 12-inch chapter in Stark, basically. Those will be scoring at home, except this pulls out to 7 days, not 24 hours. Okay. We test the same people in every single combination. This is very common. This is a 2 by 3, and they're both within. Yeah. It's not that complicated. So you can see that this would be something, and in fact, many of you in this room have heard me talk about an experiment just like this in the memory class. But you can see this is a kind of experiment. This isn't a complicated experiment. This isn't some weird thing that no one would ever do. This is totally sensible, right? And why would you do this? Well, you want to watch. You want to see forgetting, right? Different retention intervals, and you want to have 2 different kinds of memory tests. It's completely sensible to do this. This is completely fine. There's no issue with this. What's the model look like? All we do, it's a 2 by 3 by however many subjects we have. Remember, we just think of subjects as another variable. And we put pi in, so it's x equals mu plus alpha plus beta plus alpha beta plus pi plus alpha pi plus beta pi plus alpha beta pi. I hate those alpha beta pi's. They're so stuck up. Every bad college movie, ever. And then the dean is really kind of crusty and he suspends you. Like deans can suspend you. Well, I think they probably can actually. When Arthur was the dean, I used to say things like that to him all the time. Yeah, you crusty old dean. And quote Animal House, this little known codicil in the Faber College Constitution, where the dean can put a fraternity under double secret probation. I'd say that things like that in the Senate, just to pass the time. I hate Senate. Not the idea of being on it. There's lots of terms here. A lot of error terms too, because we know now that error terms are things that have pi in them. They're interactions with, remember, tau by pi, those are error terms. So these are all going to be error terms. This one, oh boy, those are all, how do we know what to divide by what? Whatever will we do? We could give up now, but there's a whole month of school left. Okay, how the hell do you do this? There's a really mechanical way of doing this. It's not hard. The first thing you do is, so you make up a source of variation in degrees of freedom table. Now the nice thing, by the way, is if you do this with SPSS the way I told you, the way I'll tell you how to set it up on Tuesday, you can tell SPSS that in this case retention interval and M for memory are fixed factors and subject is a random factor, and it'll know what to test with what. So that's nice. But you know what? This is pretty easy to do. I'm assuming there's 10 people in each, all told, 10 people. N equals 10. Subjects, list that first. Subjects has 9 degrees of freedom, n minus 1. Then list the first within subjects factor you have. Well, I thought I'd list retention interval first. Why the hell not? It doesn't. I could have done memory first, memory test type, but I used retention interval first. It's got 2 degrees of freedom. There are 3 retention intervals. Then I go retention interval by subject. Oh look, there it is there. So you say, had this. Then I crossed it with the thing above it. Then you can't cross retention interval with itself, so you list the next variable. Memory. Memory by subjects, memory by retention interval, memory by subjects by retention interval. How do you know what to test with what? What you divide by what analysis of variance? You divide mean squared for subject. You wouldn't even do mean squared by subjects. Oh, it's exciting. People are different. That wouldn't be something one could do. Retention interval, however, you want to see if there's an overall effective retention interval. You would take mean squared retention interval and divide by mean squared for subjects by retention interval. That's an error term. And then for memory, it's memory by subjects. That's an error term. And then for memory by retention interval, the interaction, it's memory by subjects by retention interval. It's a thing called Yates order. It's a way of listing out degrees of, listing out sources of variation and figuring out what error terms are. And we're going to build on it to show you how to do this with any design. Right now, I've only talked about repeated measures designs, but you can do it with any kind of design you want. So you go subjects, retention, subjects by retention. Memory by subjects, memory by retention by subjects. Big brown bear. Just run into that book. One fish, two fish, one fish, blue fish. 3 names of hammer. I'm so tired of reading that to my kid. Anybody here have kids? No? One day you will read those books to your kid. Because everybody gets that set of Dr. Seuss books. Everybody does. With the cat in the hat holding it, it's plastic. And your kid will love 3 names of hammer. Because it's a fun book, but you learn to memorize it. Like, you get so bored with it. So I used to mix it up. I remember I read it to Maddie once as Bill Clinton talking to Ross Perot. I will not eat no green eggs and ham. She kept saying, Daddy, stop it! Shatner, things like that. Yeah. Would you eat them with a cup? Would you do it about? Fun. It's really not that hard, this stuff. It's, in fact, because I said, it becomes mechanical. You'll do enough of these, by the way, you'll hate me, but it becomes very mechanical to do this. And the reason, you might say, well, you just told me the software does it. Software also does what it's told. So when you tell it the wrong thing, it just does stuff. So when you, instead of having the software do it, you have the software do it, but you also work out what the error term should be yourself when you do an analysis, just to make sure you get it right. Believe me, when I get articles from journals to review before they get published, the number of times I come, this happens about 1 in every 7 or 8 that I get, someone's just done the stats wrong. Because the first thing I do is I draw the design out when I read a paper, and I just think to myself, okay, how would you analyze this? How are these guys doing this? Oh, I see they're doing this. Oh, easy, I can work that out. And that's not the right mean square. They did that wrong, or those degrees of freedom are wrong. And I just write a little polite note saying, I think you meant to do it this way. And I get back the same thing all the time. Oh my God, I'm so embarrassed. Thank you for catching that. Right? So this happens to professionals. Right? So it'll happen to you too when you're doing thesis work or whatever. It's simple to do. You break these things down. You figure out what the right error terms are, and you say, take a look and say, did SPSS or SAS or whatever the hell you're using, did it do the right thing? That's the important thing. Questions, please.
I know M is memory, but how did you get 1?
There's two kinds of memory.
Okay.
Implicit and explicit.
Okay.
Yeah. No problem. Thanks for asking rather than just letting it stew. Other questions? Yeah, please.
Could you say that again?
There's 2 kinds of memory, implicit and explicit. So you have number of levels of memory minus 1. That's how you're going to get the number of degrees of freedom.
Always minus 1.
Yeah, in this case, right now, yes. And then the interactions are whatever minus 1 times the other thing minus 1. Yeah. For now, yes. Yes. It gets a little more complicated. Not a lot more complicated, but a little bit. Okay?
So the retention interval of the times?
Yeah. Yep. That's by the time you study and test. It's just a term, retention. Yep. Other questions? You guys are all putting on cream. What's going on up here?
It smells really good.
She brought it out and then we just...
You just all started putting on cream. You're like it's like you're having a cold.
It's cold outside. It's dry today.
today.
We all
What are you having, like some sort of cosmetics party up here? And you can buy these and they're great.
It smells good.
And if you act now, we'll throw in cough drops and some chalk. Comes in a gift basket.
It's really nice. Try it. It smells good.
That's okay. It's okay. I am not confident enough in my masculinity to do that.
You can probably smell it. Well, it's a fragile thing.
I fully admitted it. See that? We're sharing. All right. Any other questions? If anybody wants to buy cream, I think these guys have an affiliate link. Quick.
Is that weird? I feel like everyone does that. When someone like brings out like cream or like...
It's even more than you know. It's weird. It's just breaking out cream. That's the weird part. On that note, guys, thanks.
I thought that was normal.